Alright, this video is the continuation of the buffer video, and we're going to talk about buffer capacity and the pH range over which buffers are successful, and then how do we calculate the pH after a strong acid or a strong base is added to a buffer situation. Okay, so the first part of this is a discussion of something called buffer capacity. So I will define that. Okay, so as we have been taught, a buffer is a solution of a weak acid and its conjugate base, and they resist changes to pH when a strong acid or a strong base is added to a buffer. So there's something called buffer capacity, which is the amount of acid or base that the buffer can neutralize before the pH starts to change dramatically. So buffers are limited in their capacity to prevent a solution from changing its pH drastically, and the amount of acid or base that a buffer can neutralize before that pH changes dramatically is called buffer capacity. And that kind of leads into this discussion of a pH range, which you might suspect is a range of pH over which the buffer acts effectively. Oops. So within what pH range is a buffer capable of neutralizing strong acid or strong base? And so usually we can estimate this by saying it's within plus or minus 1 pH unit of the pKa of the acid. So that means, like, let's say we had remember pKa is just the negative log of the Ka. So let's say we knew the Ka of an acid and we took the negative log of it, and let's say that the pKa was approximately 4. Well, then what this means is that the pH range of this buffer solution is going to be effective over plus or minus 1 unit of that pKa. So somewhere in the range of 3 to 5 would be the pH range of this buffer. Okay, based on the pKa value. And that's just an estimate. It's just a rough estimate of where the buffer would be able to neutralize acids and bases effectively. Okay, so now what happens if we add strong acid or strong base to a buffer? So we know, of course, that strong acids and strong bases ionize completely. And so there's a couple factors that we have to take into account with how a buffer reacts to a strong acid or a strong base. So let's say we have a buffer made of HX, and then, of course, X minus, right? Conjugate acid, weak conjugate acid, and its conjugate base. Or a weak acid, and its conjugate base. So we have two situations. What happens if you add a strong acid, and what happens if you add a strong base? So let's start with the acid first. So if a strong acid is added to this buffer system, then what's going to happen, remember, of course, strong acid is going to give you H+, and a non-basic anion, right? So if a strong acid is added to the buffer, we have too much H+, right? So the H+ from the strong acid is consumed by the X minus ion to produce more HX. Okay, so think about the X minus is going to act just like that as a conjugate base to accept the proton and to reform the HX. So what happens is the concentration of HX is going to increase in this process, while the concentration of X minus would decrease, right? Because the X minus is going to be reacting with the H+ to make the HX. So that's what would happen if you added a strong acid. The second situation is what would happen if you added a strong base. And hopefully you can kind of see that the opposite would occur, that the OH minus, which would, of course would be coming from your strong base, like say sodium hydroxide, is consumed by the HX to produce more X minus. So that OH minus is going to react with the H plus, take the proton, and leaving you with X minus. So just like the reverse of the first reaction, the HX concentration is going to decrease because we're using that to react with the OH minus, and the X minus concentration is going to increase. So there are two reverse processes here, but I think that makes sense if you think about one is you're adding H plus and the other one is you're adding OH minus. So we're talking about pushing this reaction in two different directions. Okay, so then our discussion becomes, well, how do we calculate the pH? We have to think about this calculation in two ways. Okay, so the first thing is we have to think about the neutralization reaction that's occurring and the effect that that neutralization reaction has on the concentration of HX and on X minus. And this is kind of it's a stoic discussion. Then the second part of how to process this pH calculation is to use the Ka value of my acid and these new concentrations of HX and X minus, meaning after the neutralization has taken place, to calculate the total H plus concentration and then the pH calculation. Okay, and one way to do that is a equation that is called, hold on, I'm looking at my notes here because I can't remember if this is something we have discussed. Oh yeah, we did, of course, when we were talking about calculating just the pH of a buffer. We learned the Henderson-Hasselbalch equation was one way to do that, and so that is another example of where that comes back into buffer calculations. Is that equation will still work even after we add a strong acid or a strong base. Okay, so let's look at a practice and talk about how we would solve this. Okay, so a buffer is made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make a 1 liter solution. The pH of this buffer is 4.74, and I have looked up that Ka for acetic acid is 1.8 times 10 to the negative 5. Okay, so A, calculate the pH of the solution after we add 0.02 moles of sodium hydroxide, which of course is a strong base. And then B, for comparison, calculate the pH that would result if you added that same 0.02 moles of sodium hydroxide to a liter of water. Okay, so we're going to solve A. And to solve A, I need to write the reaction, which is going to be, so we have to think about this. I have a buffer situation, right? We know I have a buffer because I have a weak acid and its conjugate base, which was coming from the sodium acetate. Okay, so I am reacting a strong base with this buffer, which means the OH minus is going to react. And so that's going to react with the acid component of the buffer. And of course, behaving like an acid, it donates a proton. The base accepts the proton. And we end up with water as a product and acetate, the acetate ion as a product as well. Okay, these things are all aqueous with the exception of the H2O. Okay, so this is where we kind of have to consider this from a stoic perspective, and then as an acid-base calculation. Okay, so if we think about this from the stoic, we can write sequences because I have let's keep track here. I have 0.3 moles of the acid. I have 0.3 moles of the acetate. And I have 0.02 moles of the OH minus. Okay, so if we think about this as a sequence, and I'm actually going to avoid writing this as a sequence because I don't want it to confuse us too much. Well, I guess we could. So I think I will. So I have this is my reactant and this is my reactant. Okay. So if I write my sequences, it's going to be pretty obvious to figure out who is limiting and who's in excess. Forgot to underline. Okay, so what this means is the limiting is OH minus, so it's all used up, it's all reacted in this situation, and my excess is the acetic acid. But what I have to think about now is something we haven't considered before, which is that there was some of the acetate ion already present. Okay, so think about this. So before the reaction, there were 0.3 moles present, right? Because that's what the problem told us. And this reaction produces, let me change my color here so we can see it. This reaction produces 0.02 moles more, for a total moles of the acetate ion of 0.32 moles. Okay, so that's a little bit different than we've ever thought about stoic before, because we never had a product present until we just talked about this situation. Now, in kind of comparison but also opposite, I have to think about how much excess acid is left over, right? And this is like your straight regular stoic calculation. Well, if I started with 0.3 and I used 0.02, then I have 0.28 moles left over after the reaction is complete. I think that's probably easier to understand because that's just like we've done an excess problem before. But the difference is talking about the product who was present already, and then I added more to it. Okay, so then this is where Henderson-Hasselbalch comes in, and we know that equation says the pH of a buffer can be calculated if I know the pKa of the acid, plus a log of the concentration of the base to the acid. Okay, and if I look at everything, I have all of this. So I know that the pKa was, where was it? 4 points. Nope, that was the pH. Sorry. Oh, pKa. I have to find it. So pKa is negative log of the Ka. And actually, when I do pKa, here it comes out to be 4.74, I think. I think it's the same as the pH. Let me just check that real quick. Negative log of 1.8 times 10 to the negative fifth. Yeah. Okay. So my pKa of the acid was 4.74 plus my log of the base concentration over the acid concentration. And so my base concentration is, of course, the acetate, right? The conjugate base of the acid. So that was 0.32 molar. And then the acid, of course, the acetic acid was 0.28, sorry, my goodness. And so if I do this calculation, we come up with the fact that my pH is equal to 4.80, and we see, remember, that my initial pH of the solution was 4.74. So we added strong base to this, and we only increased our pH by, what is that, 0.06? Okay, that's hardly an increase in pH, where we added a strong base to this. So that shouldn't surprise you because it's a buffer, but it also should kind of surprise you because we have always been under the assumption that if I added hydroxide to something, it's going to make it basic. Well, not if it's a buffer, and as long as we don't exceed the buffer capacity of this situation. So my two pHs are very similar, and I should take away from this that, yes, that is the definition of a buffer, that it resists changes to pH upon addition of a strong acid or a strong base. And so yes, the pH went up, but very minimally. Okay, B is a very simple calculation, and they want you to see that in contrast. What would the pH be if you added that same amount of moles to just 1 liter of water? And so they said my moles were 0.02, just like in my original problem. And so if I have the moles over, it was a 1 liter situation, so that's my molarity. I can take the negative log of that. And that's going to give me my POH. So negative log of 0.02 comes out to be 1.7. And then pH, of course, 14 minus 1.7, 12.3. Holy cow. So this is what the problem was trying to get you to see, that when we added that same amount of strong base to a buffer, my pH hardly changed at all. But when I added that same amount of strong base to just pure water, my pH was extremely basic. And so that is the difference in adding, in this case, it was a strong base to a buffer resisting change in pH versus into water, which would completely make your solution